Welcome to another video. This is one of those integrals I strongly recommend that all calculus students attempt to integrate, because in the process of getting the answer to this, you will just show so much algebraic dexterity, integration skills. You'll be happy that you were able to integrate this. Now, before we go on, let me tell you what the answer to this integral is. I'm going to write the answer here. You ready? It is 1 over the square root of 2 multiplied by the inverse tangent of the square root of tan x plus 1 over the square root of tan x divided by the square root of 2 minus the inverse hyperbolic tangent of the square root of tan x minus 1 over the square root of tan x. Close the parenthesis and add c to it. You would say that looks insane. Okay, that's what we're about to do. Let's get into the video. As usual, when an integral looks too complicated or too tricky or too hand-tying, just use a u substitution. Try to change what you see into something else and see what turns out. So now what I'm going to do is go the vice versa way. I am going to use t instead of using u as for my substitution. So let's try to replace this with something algebraic, because algebra is a little easier to manipulate than trig sometimes. So let's do it here actually, because I might need to use that space. So I'm going to be erasing as often as possible whatever work I show you, just to keep the board with sufficient space. So let's say let t be equal to the square root of tan x. Okay, that simply means we can square both sides, because we need tan x actually. So the square both sides, you have tan x. Okay, just one more step. Let me square it one more time. I have t to the fourth will be tan squared x. You're wondering, why is this squaring everything? You'll just wait. Now, let's take the derivative. You can use this for your derivative, but this appears to be the easier one to find my dt and my dx, because we need to replace dx. Remember, once you change from x to t, you have to change dx to dt. So let's use this for dt. If I do this differentiation, I'm going to get 2t dt will be equal to the derivative of this is secant squared x dx. But I need to write everything in terms of dt, so I don't want dx anymore. So what do? I am going to, I can write this in terms of t, because I know that secant squared x is the same thing as tan squared x plus 1. That's a trig identity, you know, right? So we know that secant squared x is tan squared x plus 1. This is from the Pythagorean identity. So here I'm going to write secant squared x as tan squared x plus 1. We still have our dx. So it means that tan squared x, which we already obtained, that's why I did it. Okay, it's going to be t to the fourth plus 1 dx. And this is still 2t dt. So to isolate dx, it's just going to be this divided by this. So I know that dx equals 2t dt divided by t to the fourth plus 1. So therefore, I can say this integral, which is the square root of tan x dx, is the same thing as the integral of the square root of tan x is t multiplied by dx. What is dx? All of this. It's going to be 2t over t to the fourth plus 1 dt, which clearly is the integral of This t multiplies this. You're going to have 2t squared over t to the fourth plus 1 dt. This is just the first substitution. Here, this integral has become the integral of 2t squared over t to the fourth plus 1 dt. We have not started integration. We have just changed what we saw into something that looks more algebraic. Let's get rid of this. It's hard to integrate this because firstly, the bottom is not reducible. You cannot factor it into simpler expressions. And if you take the derivative directly, you're going to be getting t cubed in your derivative, which has nothing to do with t squared. So it's harder, especially because the degree of this is to the fourth. I wish it was a lower degree. So you start thinking, maybe we can reduce the general degree of what we have, which is a good strategy. And in doing that, you might be tempted to do a U substitution or some kinds of substitution that reduces the degree, but I would recommend you just divide everything by the top. Remember, the degree of the denominator should be greater than that of the numerator before you take an integral of a rational expression. It's always a safe path for you to follow. So if I divide this by t squared, I divide this by t squared, divide this by t squared, I'm going to end up with just 2 on top, t squared here, and 1 over t squared here. Let's write it that way. You're wondering, how can having an expression like this in the denominator make my life any easier? That was the question I asked the first time until I had an epiphany of something I did in high school. And we're gonna see it. Now, just leave this way. Remember, it is impossible for you to integrate this because the derivative of the bottom does not contain, is going to have a t at least, but there's no t on top unless you put a fake t here. But what if we can reduce this again through a strategy that always works? Watch this. You see these two terms, let t squared be a squared. Let's call it a squared. And let 1 over t squared be b squared. Remember that anytime you write a plus b and you square it, because we're trying to attempt completing the squares here, but it's going to be awkward. We want to fix it. So a plus b squared is the same thing as a plus b times a plus b, right? And this generally gives us a squared plus 2ab plus b squared. So this is exactly this. But if you want to get just a squared plus b squared, you have to move this 2ab to the side so that a plus b squared minus 2ab equals a squared plus b squared. Which clearly tells you that if you want to write, you see, this is a squared, this is b squared. If you want to replace t squared plus 1 over t squared, which is what we have here, we can actually replace it with this expression. But this expression will look like this: t plus 1 over t squared minus 2 times t times 1 over t. But if you multiply these two together, you're going to get 1, right? This cancels this, you have 2. So this is actually t plus 1 over t squared minus 2. So I can clearly write what I have in the denominator as this, which is what I'm going to do. However, it would not work. I need the brother to this. And what does the brother look like? The brother looks like this. Instead of writing a plus b squared, what if I had chosen a minus b squared? Let me do it here. A minus b squared. What would this be? This would be a squared minus 2ab plus b squared if I expand this. So I still have a squared plus b squared, which is what I had here, which is the same thing here. But the difference is this is going to be a minus b squared plus 2ab equals a squared plus b squared, which means that I can replace this same expression with this. That is, I can say that t minus 1 over t squared, this time plus 2, both of them constitute this, t squared plus 1 over t squared. T squared plus 1 over t squared. Now we need this. We need these two to be able to integrate this expression. Why do we need both of them? It is because the derivative of this can be upstairs, can be here. How do you know they can be there? Because you're going to put it there and take it away at the same time. Okay, so look, if you take the derivative of t plus 1 over t, what do you think it's going to be? Let's do that again, because that's what we're going to do now. Okay, these are the places where people get stuck. So what's if we make, let's say, let u be equal to t plus 1 over t. What is du? What's the derivative of this? 1. What's the derivative of this? It is minus 1 over t squared. That's it. Because this is going to be t to the minus 1. The minus 1 comes down, then to be t to the minus 2, which is the same thing as this. Okay, the same thing, let's say let v be equal to t minus 1 over t, this version. If we take the derivative of this, it's going to be equal to, we have dv is going to be equal to 1 plus 1 over t squared. It looks like they're going to cancel each other out. So what we're going to do is, instead of writing this, we're going to say this is equal to, let's write it here. This is equal to the integral of, you see, each of these u and v, they both need 1s. But when you add this to this, what do you get? You get 2. Look, if you add this to this is going to cancel this out. You just have 1 plus 1, and that's 2, which is the 2 sitting up here. So I can write this as 1 plus 1 over t squared plus 1 minus 1 over t squared. That's what's sitting on top. And what's sitting under is going to be this one, t squared plus 1 over t squared dt. So you're wondering, why am I not using any of the things that I have done? Just remember, this is all we need. Okay, everything else that I've done is just to show you the path to where we're going. Now, let's use it. So now we know that I can actually split this into 2 different integrals so that what I have will be equal to, this goes here, will be equal to the integral of 1 plus 1 over t squared divided by t squared plus 1 over t squared, okay? And it's going to be dt plus, I do another one, the integral of 1 minus 1 over t squared divided by, so why am I not writing the denominators? I am not writing the denominators because I need to decide which of these versions I'm going to put there to make the integration possible. Remember that if we make u t plus 1 over t, the derivative of u is this. Where is this located? Top. So this is where I must put u. So I have to use this version, the u version. Okay, this one, the positive version. So here I'm going to write t plus 1 over t squared minus 2. And here I have to write the v version, which is t minus 1 over t squared plus 2. Nice. And because we already did the work for the u and v substitution, see what I'm going to do? I'm going to say that the denominator that I have here is v squared plus 2 And what's on top of it is going to be dv. I forgot to put the dt's. So I'm replacing all of this dt with just du, all of this dt with just dv, and that's what I have, plus the integral of du over u squared minus 2. Now, any integration learner should be able to integrate both of these. Okay, let's get rid of this. So you start thinking, how do I integrate this? This is beginning to look like that arctan integration. And this is going to look like, hey, I can do difference of 2 squares here if I can make it a perfect square. I mean, difference of 2 squares, and then I can do log. But you can do log, but you can also do hyperbolic tangent, which after you're done is the same representation as what you would get if you did logarithms. So what I'm going to do is rewrite both of these this way. I'm going to factor out 2. Okay, so I'm going to write, each of these is going to be 1 over 2. It's going to be 1/2 of the integral of dv, watch, over, this is going to be, because it's the addition form, it's going to be v over 2 squared, v over square root of 2, not v, yeah, v over square root of 2 squared plus 1. Okay, if this confuses you, all I did was divide everything here by 2. Or factor out 2 in the denominator. If you factor out 2, v squared plus 2, if you factor out 2 just in the denominator, to factor means to divide, okay? It means I have divided this by 2. So what is here is going to be 1, because if I return the 2, it's going to go back to 2. And what is here can no longer be v squared. It has to be v squared over 2. But because I want to put everything in the same square, I write this 2 as the square root of 2, and then I square everything. So it's now v squared over 2, which is what I got. But if I remove this parenthesis and distribute this 2, you're going to come back to this. So that's the strategy you use here. And I'm going to do the same thing in this case. So don't get confused. So I'm going to have plus 1/2. The same thing, the integral of du over, this is going to be v over, sorry, it's u this time, u over the square root of 2 squared minus 1. Okay, those are the two integrals written nicely. Now, can you integrate this? Remember that arctan substitution? That's where you get your answer. Okay, but I think I want to do this one because most people are not familiar with this one, but you can do the same exact thing in integrating this. So let me write the answer to, let's not write the answer, let's do the calculation for this one. So for this, I'm going to do the hyperbolic tangent substitution. So watch. So ignore this 1/2 and let's focus on the denominator. I'll say let u over the square root of 2 be equal to hyperbolic tangent of theta. When the sign is a plus, you use tangent. When the sign is a minus, you use hyperbolic tangent. Or you can do partial fraction decomposition, which may take too much work, but you never know. That depends on you. But I like the hyperbolic tangent because it's very analogous to the tangent one. So if I do this, then I'm going to say that that means that u is equal to square root of 2 hyperbolic tangent of theta. So what is du? Du will be equal to, I've taken the derivative of this. The derivative of this is I'm going to have the square root of 2 left, but the derivative of hyperbolic tangent is hyperbolic secant. Okay, it's just very, like I told you, it's like secant squared, but it's squared. So it's going to be hyperbolic secant squared theta, which I call sec squared theta. One thing I also know is that hyperbolic tangent, because this is squared, hyperbolic tangent squared minus 1 Well, if we had flipped this, it would have been the same thing. But because now it is 1 minus hyperbolic tangent theta, it is negative sec squared theta. That's what this substitution is. So that means if I go to this expression here, I told you this is going to really try how much you know. Okay, so here we have du. We already said du is this. So we have the square root of 2 sec squared theta over, this is going to be tan squared theta minus 1, which we said is negative hyperbolic secant squared theta. Okay, d theta. Look, this cancels this. What you have left is just negative the square root of 2 d theta. Let's put that under the integral sign. And if you take this integral, it just means your answer is negative square root of 2 theta. Since we said that this, where is theta? That this is inverse, is a hyperbolic tangent theta. In order to get your theta, you just have to take the inverse hyperbolic tangent of this. So from this, we can say that theta is equal to inverse hyperbolic tangent of u over the square root of 2. That's what theta is. So this whole thing can be written as 1/2 times negative square root of 2 times inverse hyperbolic tangent of u over square root of 2. But we know u itself was a substitution that we made to replace this guy. And v was a substitution we made to replace this guy. I copied the substitutions that we made in this corner. Remember, you could just pull out the answers to these integrations by just looking at the integration table, but I just wanted to show you the alternative to this one instead of partial fraction decomposition, and that was a good way. So now we know that our individual answers for this one, it's going to, okay, in fact, both of them have 1/2, so I'm going to pull out the 1/2. And I know that when we integrated this one, we ended up with negative square root of 2 theta, right? Negative, let's write it here, negative square root of 2 theta. When you do this one, the same exact process, you're going to end up with the square root of 2. I used phi for that substitution. So that's what we have. All you need now is to know what theta and what phi are. Okay, so let's see. What would theta be? Well, in order to get theta, you have to take the inverse tangent of inverse hyperbolic tangent of u over square root of 2. But remember what we said about u was this. Let's write it. This was the answer I wrote at the beginning. It is 1/2 giant parenthesis. But both of them have square root of 2, so I can pull that square root of 2 here, right? Rad 2 over 2 is 1 over rad 2, right? So what will phi be? Because what we have left is just phi. You know, let's clean this up. This is going to be 1 over rad 2 of phi minus theta. Nice. Okay, so what will this be? If I take the inverse tangent in order to get my phi, it's going to be inverse tangent of v over square root of 2, which is going to be the inverse tangent of v over square root of 2. So I'm going to write this over the square root of 2. But what is v? This is v. V is t minus 1 over t. T minus 1 over t is square root of 10x. So it's going to be the square root. I think I must have mixed up the signs when I started the first time. So it's going to be the square root of 10x minus 1 over the square root of 10x. That's it. That is the first part of the answer. Let's centralize this. Square root of 2. Nice. Minus the inverse hyperbolic tangent of the square root of tan x plus 1 over the square root of tan x divided by the square root of 2. Plus c. If you learned something, leave a comment in the comment section. And like the video, share the video, and be subscribed if you're not. Never stop learning. Those who stop learning have stopped living. Bye-bye.